Bright Tuty. Every student matters.
You have studied about Newton's first law of motion, Newton's second law of motion and Newton's third law of motion, right? We'll be talking a bit more about momentum. Now, what exactly was momentum? We have already studied. When we talked about momentum, we said that momentum is equal to the product of mass and velocity of a body. This momentum we have denoted with small p, as we know, mass with small m. Now, if the initial velocity of the object was given, then in that case we will take initial velocity and this will be the initial momentum of the object. Again, if the final velocity is given, we will represent final velocity will v, and then p is equal to m into v will be the final momentum of that particular object. We have studied the second law of motion, which states that force is required for the rate of change in momentum. So, the momentum is the product of the mass and velocity, and we have seen the initial and final momentum, and force is required for changing the rate of momentum, right. Now, we will assume that there are two bodies which are having some momentum and they collide with each other. Now, what exactly will happen to their momentum? We will see through a video demonstration. This is the law of conservation of momentum that we will study. Let us see what exactly the law of conservation of momentum states. Now, this is the law of conservation of momentum. Now, this law of conservation of momentum, how to define it? It says that in a given system, the sum total of momentum is a constant quantity provided no external force acts on the body. Or we can also say that in a given system, when two or more bodies interact and no external force acts on them, then the total momentum of all the bodies is conserved. That means the momentum will remain the same, and in order to prove it, let us take an example. Consider two marbles A and B of masses m1 and m2 rolling towards each other, as you can see, and let be their initial velocities u1 and u2 respectively, such that no other force is acting on them, right. So, these two marbles are coming in with each other and these marbles collide with each other such that the time of collision is for t seconds. Now, after the collision, let us imagine that velocity of marble A, the final velocity is v1 and marble B is v2 respectively. Now, very importantly, when we are talking about the initial momentum of marble A and the initial momentum of marble B, we can relate that the change in momentum of marble A in time t seconds will be given as final momentum minus initial momentum. The final momentum, as we have studied, of marble A with mass m1 and velocity v1, final velocity v1 is given by m1 v1. The initial momentum will be m1 u1. So, we can take m1 common and we can just write it like this, that is equal to m1 in brackets we can write v1 minus u1, as we have taken m1 to be common. Now, when we talk about the rate of change of momentum of marble A, that can be represented as m1 v1 minus u1 in brackets divided by t. And since the rate of change of momentum of marble A is actually the force exerted by the marble B on the marble A, therefore, we can just relate that force exerted on the marble A, that is to be expressed as F1, which will be equal to m1 in brackets v1 minus u1 upon t. Let us take us to be equation number 1. Now, this what we have seen with marble A, similarly we can calculate with marble B. The change in momentum of marble B in time t seconds will once again be given as same m2 v2 minus m2 u2, right, which can be expressed as taking m2 common v2 minus u2 in brackets. We know that m2v2 is the final velocity of marble B, m2u2 was the initial velocity of marble B. So this is the change in momentum of marble B in given time t seconds, right? Let us take the time to be t seconds, which is the time of collision. Now, as we have calculated in the case of marble A, when we talk about the rate of change of momentum of marble B, we'll also express it the same way we have expressed in the case of marble A, right? How? Let us see. The rate of change of momentum of marble B will be given as m2 v2 minus u2 in brackets divided by t. As the rate of change of momentum of marble B is actually the force exerted by marble A on the marble B. So we can say that the force exerted on the marble B, we represent it with F2, this is equal to m2 v2 minus u2 in bracket divided by t. Now we know that Newton's third law of motion says that forces exerted by two objects are equal and opposite to each other. Therefore, we can say that the forces exerted by the marbles on each other will also be equal and opposite. Now, the force exerted on the marble A is equal to minus force exerted on the marble B. This minus sign, what does it say? That these two forces are equal, F1 is equal to F2 and they are also opposite to each other. That is why we have specified this minus sign, okay. So, F1 is equal to minus F2. I hope you are able to relate why we have put up this minus sign and what is the significance of it, right. F1 we have taken from equation number 1, which was equal to m1 in brackets v1 minus u1 upon t. This is equal to F2, which is in minus, and F2 from equation number 2, as we can say, we can see that we can take m2 in brackets v2 minus u2 upon t. So this is basically because of Newton's third law of motion. This is to be specified, right? This is the derivation that we are doing, and we need to specify why F1 is equal to minus F2 because of Newton's third law of motion, right. So now we have got these two equations. We know that the time of collision was same, so this t can be cancelled out in the equation. As we can relate, we can cancel out this particular t. So now the force exerted on marble A, which was equal to force exerted on marble B, after cancelling out the t, we can equate as m1 v1 minus m1 u1 by opening the brackets will be equal to minus m2 v2, and minus and minus sign will become plus and it will become m2 u2. Therefore, we can say that m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. Now, m1 u1 plus m2 u2 is the total momentum before collision of the walls, whereas m1 v1 and m2 v2 is the total momentum after collision of the balls. Therefore, we can say that the sum total of momentum does not change or is conserved. This is exactly what the law of conservation of momentum states. Wherever we get the law of conservation, this word conservation is specified, we always relate that whichever conservation we are talking about, that conservation, whether it is conservation of mass or the law of conservation of energy or the law of conservation of momentum, this states that the sum total will never change and it is conserved. So I hope you must have enjoyed this beautiful video animated activity and you must have understood. Try to relate it once again. What we have taken up here is, let us take another example, not of the balls, or we will take the example of any two cars. Let us say that there is a car A. Fine. Now, this car A, let us say the mass of this car A is represented as m1. The initial velocity with which it was moving is taken to be u1. Got it? And there is another car B with mass, let us say m2, and it is also with the initial velocity u2. Fine. Now, if we calculate the initial total momentum of both the cars. What does it mean? I am talking about the total initial momentum of both the cars. It simply means that I'll be taking the initial momentum of car A plus I'll take the initial momentum of car B. Now, what will be the initial momentum of car A? That will be P1 plus initial momentum of car B, let it be P2. Now, this P1 is basically equal to M1 into U1 plus the initial momentum of car B will be M2 into U2 because momentum is mass into initial velocity. Now, let us take this situation that these two cars collide with each other. Now, when they will collide with each other, obviously their speeds are not going to remain the same. They are going to either increase or that is going to decrease. So, let the final velocity of car A after collision be V1 and of car B let the final velocity be V2. Now, when we take the final total momentum of both the cars, I am taking the final total momentum of both the cars and that will be equal to what? The final momentum of car A plus the final momentum of car B. The final momentum of car A will be m1 v1 because it is the product of mass and final velocity, and the final momentum of car B will be m2 into v2, right. Now, this is what we have seen. Let us try to relate. There is a car A moving with an initial velocity mass m1 with initial velocity u1 and a car B with mass m2 with initial velocity u2, right. They collide with each other, after which the velocity of car A becomes v1, that is the final velocity, and the velocity of car B becomes v2, the final velocity, right. We will take the total momentum of both these cars before the collision, that is taken to be initial, and we'll take the total momentum of both the cars after the collision, that is final momentum. The initial momentum will be the sum total of the initial momentum of both the cars, that is m1 u1 m2 u2, and the final total momentum of both the cars, that is the sum total m1 v1 plus m2 v2. Now, law of conservation of momentum states that these are equal. Try to relate, my dear students, what exactly law of conservation of momentum states. It states that the total momentum of two bodies before collision is equal to the total momentum of these two bodies after the collision, right. And because these two momentums are same, that is why we can say that there was no change in momentum, or in other words, the total momentum remains conserved. This is the law of conservation of momentum that we have seen through this animated video and through this example also. This is quite important. It is a 3-marker question. You need to derive, you need to practice, because in exams you will get derive the equation for law of conservation of momentum. Got it? This is quite important.